All right. Welcome back, everybody. You all survived. Hello. Anybody out there? Echo, 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 echo. Does that seem awfully loud, or is that okay? All right. So I'll talk a little bit about the exam later, but you probably don't want to hear anything about it right now. So if you remember last time, we started talking a bit about caching. And basically the point of caching is to make use of the principle of locality to act like as fast as the smallest thing and as big as the biggest thing. Okay, and the reason you need caching is because by physics, the bigger something is, the slower it is, and you just can't get around that. Okay, and I kind of showed you this as a schematic of the modern memory hierarchy of a system, and believe it or not, this is already old. Forget the... So this is already old. We have third-level caches now that are available on chip. All right, so pretty amazing. Wow, that's actually echoing. Let me turn this down a sec here. All right. Can you still hear me? That's a little less echoey. But anyway, so the idea here is we want to be as fast as registers, let's say, and as big as, well, disk or tape, although tape isn't used too much anymore. By the way, let's close our laptops. New rule. No laptops, no phones. So we talked about some of the sources of cache misses last time, and we actually talked about 4 C's, but there's actually 5 you could come up with. So the normal ones they talk about with regular caches are compulsory, capacity, and conflict misses. And compulsory miss, or a cold start miss, is basically the first time you see something, it can't possibly be in your cache. Okay? Unless what? What might be a way that it could be in your cache even when you haven't looked for it before? Yeah. Prefetcher might do something. Okay, yeah. Well, but then it won't necessarily be in your cache. So putting something into your cache is actually what we're talking about here. A capacity miss is basically when you've pulled it into your cache before, but it's no longer there because you didn't have a big enough cache and something got kicked out. A conflict miss is basically if you brought it in before, but it got kicked out because your cache has lower associativity than fully associative. Okay, and I'm going to remind you in just a second what a two-way set associative cache is, and you'll see where conflicts come from. And then a couple of other ones. I only mentioned coherence misses last time. The idea behind a coherence miss is you got 2 processors. One of them brought it into its cache, and the other one wrote it. And what you'd hope to have happen is that the hardware automatically invalidates the first cache. I guess go in the direction you've got. First one read. Second one writes, first one gets invalidated so that when the first one goes back and looks, the data isn't there. And the reason we want that invalidation to happen is because otherwise the first one's going to be reading old stuff out of its cache that's no longer coherent. Question, yes?
So there's a copy of the same entry in the cache in both processes?
Yeah. So yeah, in this particular scenario, caching is used on both processors. They both at least have a first level cache. And if processor A loads something into its first level cache and processor B writes it in its first level cache, we now have inconsistency unless somebody takes care of it. And oftentimes there's hardware that takes care of it. And so that would be a conflict miss when you go, or a coherence miss when you go back to look for it. Something which we will talk a lot about sort of starting with the end of this lecture and going on to the next one are policy misses. And these tend to be only talked about in operating systems classes. The first 4 here can be talked about both in hardware and software domains. But a policy miss is a miss that happened, you pulled it into your cache, it got kicked out because of some policy, and you go to look for it later and it was a suboptimal policy. It should have still been in your cache. All right, we're going to talk about a lot of different policies that we could consider. All right, any questions on these? Yeah. Well, a capacity miss is not going to fall under a policy miss, because the way to think of a capacity miss is a fully associative cache, you just couldn't shove anything more in. And, you know, I guess the way that a capacity miss could fall under a policy miss is, I guess I'm assuming LRU here, and we'll talk more about that later. So, okay, so in that instance, it would be a policy-related miss. But usually when you talk about LRU and standard associativity, then they don't bother to call it a policy miss because that's kind of, you know, ho-hum, no, ordinary stuff. Any other questions? Can anybody give me an idea how you might tell the difference between a conflict and a capacity miss? Other than reading what my slide said? Yeah.
Conflict miss, there could be more space in the cache. It's just that this specific entry can't go in the
Yeah. So what's an experiment that could distinguish between the two? Yeah.
You can make these practical associativity so that
Exactly. So you have to talk of this as a thought experiment. Assume we had a fully associative cache. We see all the misses. Then we go to a two-way set associative. Misses that are new because of going to two-way set associative are called conflict misses. So this is usually a thought experiment involved there. All right. So the only reason I bring these up is sometimes when we're getting a high cache miss rate, which we could potentially do when we're paging a lot, we might try to figure out which type of miss it is, and then if we know which type of miss it is, we could possibly fix it. Like if it's a compulsory miss, then maybe we put a good prefetcher in there. Or if it's a capacity miss, maybe we try to add more memory. Okay, and I'll show you what that means a little bit later. It's not quite as odd as it sounds. Okay. So then finally I reviewed something which probably you got in 61C, which is a n-way set associative cache. And here we're going to do two-way. And in the case of two-way, you basically take the address, and we divide it into some pieces. Now, there were some questions, some good ones last time about, well, gee, when we talked about paging, we had an offset and the page ID. This looks like a different division of bits. What's the deal? Well, yeah, you divide the same bits up in different ways, and we'll look at how we can intersect these two ways in a couple of slides. But when we're talking about caches, here's an address that's 32 bits. The lower part is the cache line, which is exactly like a page offset, although they're usually smaller. So a cache line is maybe 32 to 128 bytes, so that might be 5 to 7 bits down here. The cache index is pointing at which one of the sets should we look in, and then the tag is used to see whether the thing's actually in the cache. So I have a little animation I showed you. You start by taking the index bits, and that shows you which, in this case of the two banks, which line in each bank could be possibly our thing we're looking for. We now take the tag, and we compare the tag on either side. So this is a comparator. And one of them, let's say, matches, which will basically cause this mux to grab the value that matches and get us our value out. Okay, so the idea here is in a two-way set associative cache, the sets have two possibilities. We look at both of them, and if either of them match, we get our result out. Okay? Now you may ask yourself, well, let me ask you, which of these three fields, tag, index, and byte select, depend on the size of the cache? Yes? Say again? Index certainly depends on the size of the cache. Anything else? Okay. Well, byte select usually depends on the size of the cache line, so that's like a sub-piece. So it's not, typically when you make the cache bigger, you don't necessarily change this piece. How about the tag? Does that depend on the cache size? Yeah, well, because you make the index bigger, you take away tag bits. Okay? What depends on, suppose we keep the cache size constant and we change the associativity. So we go to a four-way set associative cache. Then what happens? Index gets smaller? Yes. Why is that?
because now you're four-way, so there's less blocks to get to choose from.
Yeah, the exact way to think of that is if we keep the cache the same, this cache size has to do with the total amount of space here. If we go four-way set associative, each one of the banks is smaller by half, and so basically we lose a bit in the cache index by going from 2 to 4. Okay, this is all hopefully review to you guys, but if you have any questions, ask them now or forever stay lowest associativity. Yeah. If you're keeping the cache size constant, then that means the total amount of data in whatever banks you have stays constant. So when we go to four-way set associative, that means we have 4 banks, each with half as much as we had before, because the total size is constant. And so therefore, this index is going to lose a bit, because we have half the number of blocks in each bank. Yeah.
Does the cache tag that's stored along in each set, right, is that part of the cache size?
No. Good question. So when we talk about the cache size, are we counting the tag? And the answer is no. So typically, when you talk about an 8K or 64K or 128K cache, you're only talking about the data, and the tag is like overhead, as far as that number is concerned. Okay. And notice, by the way, it's not that there's a tag per set. The dotted line is a set. It's actually a tag per possible entry. Okay. Good. Any other questions? Okay. So now, by the way, you can see where conflict misses come from, because in this arrangement, if you can have 2 addresses that have the same index but are different because the tags are different, those 2 addresses have 2 places to sit, right? They could be here or here, and so that uses up those 2 places. If you have a third address that has the same index, now you got a conflict. Even though the cache is not full, you're conflicting on that one set. Okay? Good. Fully associative cache. Basically, you throw out this whole indexing idea. It goes to 0, and you have a single bank with everybody's got a tag and everybody's got a comparator, and you compare and parallel everybody, and you find one that matches. That's fully associative. Okay, good. So we also briefly put up this slide. So now that you know what all these terms are for sure, here's some address space. Here is a 8-entry cache. If we have direct map, that means that, for instance, this line, address 12, has exactly 1 place to go because it's direct mapped. If it's 2-way set associative, there's 2 places for it. If it's fully associative, we can put it anywhere in the cache. Okay? Good. So today I want to finish the discussion of caching and TLBs, and then we'll get into paging. So which block should we replace when we miss? So back to what is a miss. A miss is I go to look in the cache, it's not there. That means I'm bringing something from lower memory, lower parts of the system into the cache. Well, I'm probably kicking something else out. That's called replacement. What do I kick out? Well, in the case of direct map, we have no choices involved because there's only one place that this new item can go, so clearly we're kicking the old one out. Okay? If it's set associative or fully associative, now we've got some choices. So let's go back to our 2-way set associative. Now we bring a third thing in. We've got one of 2 things to kick out. Which one? Well, we could randomly pick one, or we could pick the one that was used least recently. Okay, which one of these is better? So why does it depend? Okay, so the argument here is that depending on what your data is, there are some data patterns for which LRU is the wrong thing to do. Okay, I'll buy that. Go ahead. Other comment? Okay, good. So we've got a couple of things here. So the comment there was that large enough associativity makes LRU very high overhead. Good. Hold on to that thought. Let's go back to just the algorithm for a moment. If I didn't have particularly random patterns, which hopefully our world is not that random, otherwise caching doesn't work in the first place, which one of these is probably better for a larger number of access patterns? Okay, probably LRU. Now I state that out with giving you no evidence other than, well, if you haven't accessed it in a long time, maybe you won't access it again, and you're more likely to access something if you've done it a little while ago. But, yeah, so who knows? But what is kind of interesting is, so LRU is something you might want to go after, but as was pointed out, it has a high overhead to it if you're building it in hardware, okay? Because the number of bits that you need per cache line actually kind of grows as the square of the associativity. And so oftentimes, and I'll draw that for anybody who wants to ask me after class or some other time, but it turns out that, why waste hardware if you don't need it? And what's kind of interesting is that as your cache gets big in hardware now, I'm talking about a hardware cache, you can kind of see that the difference between LRU and random is almost not worth mentioning, and we're talking about how many misses there are. So this is the miss percentage here. Okay? So in fact, if you have a higher associativity in hardware, they often just use random. They have sort of a continually running pseudo-random bit generator, and they grab a random one to kick out. Yeah?
Couldn't you just take the hardware space that you would need to implement the LRU policy and increase your cache size?
Yeah. If you have options between doing LRU perfectly and having a bigger cache, it's probably better to have a bigger cache. So that's another argument for random. Okay, now this argument, so what I've just shown you here is the best way to ever demonstrate something with data. Now you might ask, what is this data? Well, this is some, set of benchmarks run on some machine, right? And I haven't told you what it is, but I will tell you that this particular property shows up a lot in the case of hardware. And what's important in the hardware case is that although it's expensive to go to DRAM, it's not that bad. So being a little less perfect in our replacement policy is okay if it's faster. In the case of paging, which we'll talk about in a moment, what do we do when we miss? We go to disk. That's really expensive, and so we're not going to want to do random page replacement when we get into paging. We're going to want to do LRU, okay, and that's going to be our goal. Yes? Exactly. So what's missing is the latency. Okay? So let's go on here and talk about a few other. I'll talk about the latency in a second here. So now let's ask ourselves, what happens when we write? Well, one option is called write-through. So the idea here is you're going to write a data item that's in the cache. What happens is not only do you write it in the cache, but it writes all the way through to DRAM. That's called write-through. Okay? The other option is write back. With write back, you only write into the cache, and in that case, your data is more up to date in the cache than it is in the DRAM. Okay? So what does that mean? That means when you replace something from the cache and it's a write back cache, you've got to make sure you write it back to DRAM first because it's the most up-to-date copy. Okay? Somebody tell me why you might want to do write through and why you might want to do write back. Why might you want to do write through? What's the biggest advantage there? Less concurrency issues. Why is that? So with write through, then it's possible that if we have more than one processor, that it's more likely to see the up-to-date value. All right, I'll buy that. What else? Yeah.
With write-through, since you're writing disk more frequently, more of your data is on non-volatile storage.
So I didn't say disk, and in fact, let's say DRAM for a moment. So we'll bring that disk back in a second here. Yes. It's a lot simpler. There's no bookkeeping. And what else about replacement? Go ahead. That's right. When we replace with write-through, we can just throw things out of the cache anytime we want because the memory is always up to date. Why might we want to do write-back instead? Yes? So one good thing is if we change the same data a zillion times, we don't want to be bothering the DRAM with it all the time because we're just updating it. Great. And that actually means we're keeping the bandwidth to DRAM down. Okay, why else might we want to use write back? What about performance issues? Yeah. Makes writes a lot faster. Okay? The reason we put a cache in the first place is DRAM's slow. If you're writing to it all the time, it's a problem because you're holding the processor up. Now, usually people put what's called a write buffer in front to make it a little faster, so you buffer them up. But let's go back to that statement mentioned earlier about disk. Do we want to write through to disk? No, ever, never. Okay, and the reason we don't want to write through to disk is exactly because we're going to hold the processor up to the speed of the disk. Okay, million instructions to do a disk access. Okay, we've just slowed the processor down a lot. All right, so good. Okay, yes, question.
Do you have a write-back policy? When you do like a write to memory, if your block is in cache, do you guys still yield, even though it can get, it can go to memory in just a few instruction cycles?
So rarely, if ever, do you have a situation where the processor will ever yield on a cache hit or miss. So that's basically not done. Okay, so when the processor goes to do a write, if it can write it immediately into the cache, it's a fast write. If it goes to write it and it's a cache miss, it's a slow write. And actually what really happens in a modern processor is they buffer all that stuff up anyway. And so usually the stores are never held up for that unless buffers fill up. Okay. All right, so I've been kind of mixing up intentionally here the realm of hardware and software. When we start talking about caching in the domain of paging, which one of these things we choose is going to be very obvious. We're going to do write back. Okay? Modern processors in the hardware level actually typically do write through from the first to second level cache because that's all on chip and fast, and then they do write back going from second level down. Question? Yes?
As you mentioned, write back, if you're updating the cache a million times, so we don't want to write back. When do we decide to write it back to the memory?
So the question is, when do we decide to do a write back? And typically that's deferred until we have to kick it out. So somebody else is needs that cache line. At that point, we write it back to memory.
Delays or comes to L1 and L2, but also depends on if it's inclusive or exclusive, what you have in L1 and L2.
True, and yes, there's a lot of other details that one could go into at a hardware level here. Yeah. Okay, any questions? Yes?
Does write through and write back, like the motivation change when we start going to things like multi-core, where you've got multiple
Yeah, you know, when we go to multi-core and we have a lot of CPUs, so let's go toward many core, you're mostly going to do write back at the level just before the processors communicate with each other, because otherwise you're trying to broadcast every write to every processor. And so that, while it makes the coherence problem harder, there are ways to solve that. What you can't solve is you can't get around physics. So broadcasting your value to every processor is in general a very bad thing unless you have a bus. And that's the one sort of structure that you can do that with cheaply, and I say that in quotes, but you can't put very many processors on a bus. So usually write back is the domain there. Yeah? Yes, there is a form of a bitmap as to which bytes, well, at least which cache lines are dirty, not always which bytes. Okay, good. Yes?
Can a process choose whether or not it wants information cached?
Yes, processors usually have special loads and stores that say don't cache things. That's often available. Yeah. So the reason write back, actually, I probably could have brought up a slide with cache coherence that would have made great sense here. But the thing about write back is the most up-to-date copy of data is in the cache. If you have two processors, one of them writes to their cache, now they have the most up-to-date copy, and the other processor has no way of knowing it. I mean, yes, they have their own separate caches. And so when we have that scenario, then you have to have what's called a cache coherence protocol, which tracks all the writes and reads and makes sure you never get a situation where a processor sees an old value. And that's a very interesting topic in and of itself, but it's a little off topic at the moment. Yeah, one last question. Yeah. Write back makes shared memory more complicated, but it's more bandwidth efficient, so they do it anyway. Okay, good. So, cache performance is not about miss rate. It's really about how your miss rate and your miss penalties fit into play. So if you were in 152, I'd give you this cache equation, which basically says the time for the CPU to execute is instruction count times average cycles per instruction times cycle time. And the average instructions per cycle, this is 152 I'm pointing at right there, which is off topic. But what's kind of interesting for us is sort of the number of average memory accesses per instruction times how often they're missing times the penalty when they miss. And that's basically what's going to cause us to be slow. And so from this class's standpoint, what's much more interesting is what we call average memory access time. And what I'm going to do is I'll refactor this part of the equation to average memory access time times memory accesses per instruction. What's average memory access time? Well, here's the equation I showed you last time. So it's the hit rate times the hit time plus the miss rate times the miss time. So this is basically like an average time to go to memory. So if I ever ask you kind of what's the average memory access time, you're going to want to know what's the hit rate, how long does it take to hit, and how long does it take on a miss. Okay. Now, I usually factor it this way, because typically on a miss, first you have the penalty of pulling it in the cache, and then you access it again. Okay, so that's why this is probably even more useful as an average memory access time, is you always have a hit time plus how often you miss times how expensive it is to miss. Okay, and this is probably a more useful equation for this class. They're equivalent. And of course, then we could talk, if we're in 152, about, well, what fraction of accesses are instructions and what are data, and then we could have different hit and miss times for data and instructions, and yada, yada, yada. Okay. Now, just wanted to put up one last thing. Suppose we've got two levels of cache. Well, average memory access time at the first level is the hit time at the first level times the miss rate at the first level times the miss penalty at the first level. But what's the miss penalty at the first level? Well, then we try to go access at the second level. Okay, so basically the miss penalty at the first level is the average memory access time at the second level, and so we just do this recursively. Okay, so when we miss at the first level, we go ask the second level, and it will miss some fraction of the time, which will have to go to DRAM. And so you could build this equation recursively for n levels. Okay, and I don't want to go any more into this other than stop right here, but are there any questions on this? Does this make sense to everybody? It's basically, how long does it take when it's good and you hit in the cache, and then when I miss, what's the penalty? Those are the three terms, and if you can figure those terms out, you're good to go. And if you ever asked a question, pretty much you can almost answer it by figuring out what these terms are in almost all circumstances. Okay. So how does caching apply to translation? Well, translation takes time. Okay, you guys all got to draw a two-level page table for your test. Wasn't that exciting? And the problem with looking data up in a page table is there's several DRAM accesses involved there, right? You go to the top of the page table, you look something up. You go to the next level of the page table, you look something up. You find out what the page is, and then you go look up your final data in the page. So a two-level page table, you've actually got 3 DRAM accesses on a load or a store, as far as I've described it. That sounds bad. If you were a hardware architect, you would shiver. All right, I just made things really bad and slow. So what do? We cache all our translations, right? So when the CPU takes its virtual address, we don't go to the page table. We say, do we have the translation cached? Hopefully the answer is yes. We get a physical address, and we immediately access memory or the cache, and we're good to go. Now, when I say access memory or the cache, I'm really talking about the kind of caches we just got done with. So we have the CPU. It does its translation. It finds that it's cached. It goes and looks up the value at the physical address, and usually the cache that we just talked about is also in here. Okay, so we're actually got 2 caches, a TLB, which is a cache on translations, and a hardware cache, which is a cache on data. Yes?
Does this mean that the cache always has to have a physical address?
So the question, which is a very good one, is does this mean that the cache always has to be a physical address over here? So the answer is no. You can actually put the cache, you can hang the cache off here if you want, but that's got other issues. I'll maybe mention that a little later.
What would the TLB
Okay, so you're asking. So if we put the, no, that's fine. So if we put the cache here, then the CPU can look things up in the cache immediately without problem because the virtual addresses are in the cache. What do we do on a miss? Then we have to go to the TLB. Okay? Can anybody tell me what the biggest problem with having a cache on the virtual side? Go for it. Yeah, the real problem there is that if you have two processes, each of them think they have address 0, they will appear to be in the same place in the cache, and you actually get what are called aliases in the cache. Yeah.
How does that work in a TLB then, since it stores the translation? How does it know which two different zero virtual addresses?
Good question. So let's hold off the question on how the TLB deals with two different 0 addresses till about 3 slides from now, because I will, you either flush it or you put a process ID in there, but I will definitely answer that in about 3 slides. Good question. So if we don't cache, then we go the expensive path. So this is the point at which it's not found in the TLB. Oh, we better go to the page table and look it up, put the result in the TLB, and now we're good to go. And the next time we use a similar address, and what do I mean by similar there? Yes. Same page. It will now be in the TLB and we'll be good to go without translation. Okay? So we could apply our little formula we just had by saying, well, what fraction of the time do we hit in this cache? Okay? And then what's the penalty when we miss? Well, the penalty is at least 2 DRAM accesses. Okay? And so we could come up with a simple equation to figure out what is the penalty added to every load and store by the TLB, just by adding those terms in. Yes?
Do you ever store like partial results in the TLB, like a first table, first level page table lookup result?
You know, I don't think that partial lookups are ever stored. So if you miss, say, at the first level because part of the page table is paged out, that's not actually stored in the TLB. So you'd actually page that in. You'd miss in the TLB a second time. You'd page the remaining part in, and then you'd be good to go. That's a good question. So, and typically, since the kernel is allowed to do everything, there's often a way to go around the TLB as well. Okay. So the real question of whether this works is there any locality in pages? Is there locality in page accesses? Yeah, hopefully is a very good answer. So instructions spend a lot of time on the same page, yes? Okay, so that seems like that's good. Stack accesses seem like they spend a lot of time on the same page, right? Up, down, up, down, up, down. Okay, that's good. Data. Hard to say. Depends on the application, right? If you have an application that's walking through a huge array, then it's at least spending an access, you know, a bunch of accesses on each page. If you have something that's got a little tiny bit of data and it spends all the time in that one page, that's great locality. Okay, like for instance, computing digits of pi probably has great data locality. Okay, that's the signature application, by the way. I was kind of amused. David Patterson is teaching 61C in a new way. And he was talking about parallelism, and I think he had a parallel version of a Pi translator or a Pi computer that he was talking about the other day, which was pretty funny. Can we have a hierarchy of the TLB? Sure. You could have a two-level, two-level cache for TLB. You know, you look it up in the first level, and then it's not there. You look it up in the second level, then you miss and go to the page table. Okay, and this is actually called, typically at the top level of the TLB is a very small direct map cache, and then at the next level is fully associative, and that's typically called a TLB slice at the top. Okay? So what actually happens when we miss in the TLB? Well, if we have a hardware traversed page table, then on a TLB miss, there's hardware in the memory management unit that walks your page table. And if it finds the final PTE is valid, it typically fills the TLB, and the processor never knows there was a fault. The only thing it sees is that its access was a little longer because the MMU had to take over. Okay, so it's very transparent. Now, what happens if it's invalid? Well, at this point, there's nothing that the hardware can do, and at that point, it actually causes a page fault, and the kernel takes over. Okay, and that's pretty powerful because you can do anything you want on a page fault. You can pull more of the page table off the disk. You can bring something in off the disk. You can allocate more memory. You could core dump the program. By the way, is core dump because the memory was in the middle of the room? No. Where does core dump come from? Huh? Yeah, because memory used to be core memory. Remember those little donut-shaped things that look like lifesavers? That's where core dump comes from. Software could also be involved. So in this case, on a TLB miss, what actually happens is you get what's called a TLB fault. And in that case, software takes over and walks the page table. Okay, now you can see why it's very important that we have a hardware TLB cache, right? Because if we didn't, and every load or store had to go to a software handler to compute the address by walking the page table, that would be really slow. Okay? By the way, guess what Nachos has? Software TLB. Guess what you guys get to manage? Software TLB. That's Project 3. You get to ignore that until next Tuesday at least. Okay. So most chipsets, by the way, do provide hardware traversal, but there are a few that really do. MIPS, all the MIPS machines give software traversal of page tables. Nachos is modeling MIPS, and so that's why it does software traversal. It also makes for an interesting project. I think that's basically what I'm going to say on that. Any questions? So the TLB is always in hardware. Okay, the question of what you do when you miss in the TLB, that could be in hardware or software. Okay. Finally, what happens on a context switch? Well, you need to do something because the TLB maps virtual addresses to physical addresses. This was the question that was just asked a little bit ago. And the address space just changed. I went from one process to another. There's a new version 0 or new address 0. Okay, and so what do? Well, one option is you got to walk through and invalidate the TLB. And this is actually more common than you might think. There's a lot of processors, including a lot of x86 processors, where you actually have to go and invalidate the TLB. Okay, and this can get expensive if you're switching between processes a lot, but you got to do it. Okay, because the old TLB says address 0 is mapped to one physical page, and the new TLB should say, or you should say that, you know, address 0 maps somewhere else, and if you don't flush the TLB, then the wrong thing's going to happen. Can somebody tell me another place or another time other than a process switch that you might need to flush the TLB? Yeah. When you're going from kernel to user space, that's a good possibility, although oftentimes the kernel reserves a part of the address space for itself, and so you can often get by without a flush in that case. Because the user doesn't use that part of the address space, and so when you go into the kernel, its TLB entries can still be valid. But that's a good possibility. Yeah, what you want to say another one? So usually the user isn't able to actually look at the TLBs. Or if the case that there are TLB entries for the kernel, since they're marked as kernel, they'll get faulted if the user tries to use them. Can anybody think of another time we might need to flush a TLB? Yeah. Yeah. Operating system changes what page mappings are. You got to flush the page table. Yeah. Because the TLB is at cache on the page table. So if you change the page table, the cache is no longer valid. You got to flush it. Don't forget that in Project 3, by the way. Okay. Another option, which is becoming a little more common, is you just put process IDs in the TLB. Okay, and what's nice about that is that then you just leave the TLB alone, and when you change the process, it's got a new set of IDs, and so, you know, address 0 could be in there 12 times with different process IDs, and it would just pick the right one. Okay? Yeah, question?
So what's the overhead on managing process?
You mean why don't they do more of this?
Yeah, like how much hardware space is required?
So a process ID is probably 6 bits or more, and so in the TLB, you know, it's probably not a lot of space, but it's just not done as often as you might think. Yeah.
So when the kernel allocates new PID, does it have to hunt through the TLD looking for entries that might have been in the process that last user set up created?
Yeah, it needs to know. It needs to know when it's reusing process IDs, yes. And potentially hunt down old ones and shoot them up, yep. So, and basically if you change the translation table, you got to invalidate the entries. Okay, good. All right, so I'm going to do some administrivia and then we'll come back and I am going to do some administrivia. All right, so exam's not graded yet. Sorry about that. We'll try to get solutions up early next week at the latest. I will be working on them on the weekend. We'll talk about problem 3, which everybody loved problem 3, right? Well, we'll talk about that in section to make sure it made sense. Problem 3 was the in-order reader-writers problem. So they'll talk about other interesting things in lecture or in section as well, but that will be one thing that they'll cover. And I will get solutions up as soon as I possibly can format them. The joys of Microsoft Word. Project 1 reports are almost graded. We'll try to get those quickly. I know there's a couple people that wanted their final autograder results so that they can know whether their priority scheduler worked. I think that was one complaint that we had. We will do I've talked to the reader to put some priority on that, no pun intended. So we'll try to get those out. Project 2, you're working on now, of course. Sorry about this was the jam week. I apologize for that. It was the confluence of projects and exams all kind of happened. And I apologize for that. Hopefully the rest of the term won't be that bad. Any questions on administrivia? I don't really have a lot today. I dragged you through an exam on Monday. I figure I'll be light on the administrivia. Yes?
Oh, are we going to have another exam?
Yeah, so question about another exam. How many people are interested in having another chance on an exam? Ooh, okay. How many people are interested in not having another chance on an exam? How many people would want maybe an optional exam? All right. Possible. Yeah, we'll see. I don't know. It looks like there's a lot of interest in another exam. So let's take a brief right turn. I want to be talking about various interesting operating system developments on and off for the rest of the term. One of them, of course, which you're all familiar with, is Droid. It's certainly got some of the most interesting commercials out there. Not so many years ago, there was the Terminator, and such commercials would have struck fear in the hearts of everybody watching movies, but no problem. We can all become droids now, and it's okay. Android is kind of an interesting combination of Linux at the very bottom, okay, which has a lot of traditional kind of Unix structure that we've talked about, and then the runtime basically gives you Java for the applications, okay, and it's kind of it's been a useful enough combination of things, device drivers that handle communication and stuff at the low level, and interesting apps at the high level, that it's really kind of gone by storm. And it's interesting, I was just reading a couple of commentators asking, why is it that Steve Jobs beats up on Android so much? And, is it phone envy or something? I mean, that was an interesting set of comments. But how many people here have an Android phone, just out of curiosity? Oh, I should raise my hand, too. Okay, good. How many people think that a class that used Android might be an interesting class? It might be. Hard to say. Yeah. We've actually been tossing around the notion of replacing nachos with Android at some point. Oh, okay. I would say that mobile devices are certainly some of the hottest software stacks out there and the most interesting possibilities. And, you know, worldwide we have billions of cell phones, and so clearly that's an important market. I actually find it interesting that Android is finding its way into ebook readers like the Barnes & Noble Nook, into tablets, into more than just phones. And so we'll see where that goes. But anyway, so that was my little snippet on other operating systems. We may talk a little bit more about Android at other points in the future. Any questions about Android? I actually think it's kind of fun. I mean, it's kind of cool to have you know, a platform you could potentially hack, because you can actually get, you know, the SDKs are available and you can easily write apps for it. So that appeals to me. Okay. So going back to TLBs for a moment. So what organization makes sense for the TLB? And this, we've already talked about this a little bit, but kind of a very common one is you got the CPU goes through the TLB, which gives you a physical address, which goes to the cache, which then talks to memory. Okay, and this one is nice because it avoids those weird aliases where you've got two virtual addresses that are the same in the cache and it gets confused. By the way, when you put the cache here, what does that mean on a process switch? Typically it means you're flushing the cache, which is even more expensive than flushing the TLB. So that's problematic. Whatever the case may be, the TLB typically needs to be very fast, because certainly in this way it's the critical path of memory access. Okay? And this sort of argues that the TLB should be a direct mapped cache because you have fewer muxes in it, right? Remember that diagram I showed you with muxes at the bottom? Direct map doesn't have to have any muxes. Okay? Can somebody give me a counter argument to making it a direct mapped cache? Yeah, go for it. Yeah, so if we were to lay out our average memory access time equation and we were to put the TLB in there, that penalty for miss on a TLB is really expensive because we got to walk a page table. Okay, and so that would argue against direct mapped because we're going to pull the conflict misses up high in this. So that is actually why oftentimes the TLB, or most of the time, the TLB is fully associative. Okay, and what we're trying to avoid is we're trying to avoid thrashing, which is going to come up in a lot of instances in this lecture and the next. Yeah, question?
Can you explain why direct map is slower, or sorry, it's faster? Like why having more sensitivity? Isn't this all run in parallel? I mean, I don't know hardware or something. Like, does it happen? Does it work? Maybe it takes up more space. But
So I can show you very directly here. If you look, let's look at this diagram. So the question is, why is it that direct map is faster? And the answer is, what direct mapped is avoiding is, in the direct map case, you use the cache index to look up something and then you immediately use the result. And in fact, you can even start using the result before you've done the tag comparison and just invalidate. You can flush the processor pipeline if it turns out you miss. Whereas with any associativity higher than 1, which means not direct map, then you've always got to do this comparison first and then use it before you can use it. Okay? So at minimum, direct mapped avoids these muxes to the data value. Okay, now, of course, in the great tradition of standing in front of a lecture, I, of course, lied a little bit to you, because what you can do is you can actually predict which way this mux will go and have the value go immediately out. That's called way prediction. And then if it turns out that you are wrong about that, you can flush the pipeline. And so a lot of modern processors with high set associative caches at the first level, like 4 or 8, often do way prediction to predict which way it's going to go and then have an extra cycle when you're wrong. But anyway, so ignoring that, by and large, there's more stuff in a non-direct mapped case than a direct map. Question? Yes?
so TLB miss, like the penalty of a TLB miss grows with the size of the page table that it has to walk.
Yes, with the number of levels of the page table, certainly, that it has to walk. Yes, that is correct. Let's see, I think I was about here. Okay, good. So, despite wanting to have despite wanting to have it be as fast as possible, we probably are avoiding direct mapped. And the thing that I sort of continue here, consider is what if we use the low order bits of the page as an index into the TLB, then you get a problem that the first page of code, the first page of data, first page of the stack may all map to exactly the same spot in the TLB. And so you're almost guaranteed with a direct map TLB to have conflicts that you're going to be missing all the time. Okay? So this is why basically you could try to play with this a lot. You could say, well, if I pick different bits as the index or I interleaved, you could play these tricks. But ultimately, you're just not going to find a good mapping that avoids the conflicts. And so that's why, basically, high associativity. So, and how many entries? Well, 128, 256, 512 is kind of the range of pages that can be mapped. Okay? And so what it is you look up by virtual address, and what comes out is physical address and information like, is it read-write, read-only, all those bits. You remember on the test, you actually saw a page table entry, and you remember I actually gave that in a lecture. That's what comes out of the TLB, right? You put a virtual address in, and what comes out is the PTE. Okay? Does that make sense to everybody? Question? Was that email? I should have turned it off beforehand, but c'est la vie. All right, so, here's an example for a very old processor now, but here's a typical entry. You look up by virtual address. What you get out is the physical piece, whether it's dirty or not, whether it's been referenced or not. These 2 bits, by the way, are things we'll talk about in a moment when we talk about paging. Whether it's valid at all. Okay, this is when you flush your page table entries, you actually just mark everything not valid. And then whether it has read-write access or not. And then you can also have sort of an application space ID or a process ID or a couple other things in there. And so now fully associative is slower. What happens if that's too slow? Then you put your TLB slice on top. Okay. Questions? Yeah.
How can fully associative be slow parallel?
So why is fully associative slow? Because there's more stuff. It's bigger, and so bigger is slower. You've got higher capacitance.
Signal time?
Yep, the signal time is larger. This is unfortunate physics. If you take a hardware class, you start learning that bigger is slower, and that's almost always true. So, okay. So here is an interesting thing I just wanted to point out. The R3000 was a very old processor, and look where it did its TLB lookup. Here's the instruction fetch. So here's the typical fetch, decode, execute, memory, write back stages you hear about probably in 61C. Notice that they actually did the TLB lookup, took half a cycle in the beginning of the instruction fetch. Then the instruction cache lookup actually took kind of a whole cycle, but it was overlapped in this interesting way. Register file access was at the very end. And then when did we do the memory TLB lookup? Well, here we compute the effective address. We do the TLB lookup on the half cycle before we do the memory cache lookup. So by playing with the pipeline in the R3000, they were able to hide the TLB lookup in a half cycle before you went to the cache. And that was how it basically didn't impact the speed much. Okay? Now, of course, the problem with this is if you try to make your cycles faster and faster, eventually you can no longer do the TLB in half a cycle, and then you start running into problems. Okay? Now, here is another thing we could do, and I'm just going to show you this briefly because this is cool magic. But remember that question about how we map the bits between the cache and the pages? So here's a virtual address. Remember, it's got the offset piece, which is, well, how big are our pages here? Quick. How much? 1K. 1K, good. So notice that when we take this virtual page number and pump it through the TLB, we don't actually change the offset at all, right? Because the offset just gets copied. So whatever it is we're doing here totally doesn't affect these bits. So wouldn't it be cool if we could have the index lookup in the cache be only using bits from the offset. Then we could actually do the lookup in the cache in parallel while we were looking something up in the TLB. All right, let me say that again. Because these bits don't get translated, let's use these to look up in the cache while we're translating the virtual page. Okay? And this is exactly what's done with a lot of architectures. So here I'm showing actually a 4K pages. So here's a case where we take the index and we use that to look up stuff in the cache while we're taking the other 20 bits through the TLB. Okay? And then when we're done, we combine the final physical page. Well, we actually check the physical page number here that comes out with the cache tag. And then when we're done, we actually know we have the right data. Okay, so this is how we can do both TLB and cache lookup in parallel. And there are a lot of processors that do this. Of course, the problem with this sort of idea is if we increase the cache size to 8K, then what do? So if we have 8K, then suddenly we need to take this bit here and use it for the cache. So what can we do? We could predict. What else could we do that's simpler? How do we make the index smaller? That's right. So if we went to a two-way set associative cache, we could do the same hack again and go to 8K and so on. Okay. Anyway, I don't want to go into this any further, but are there any questions? Okay. Let's take a break and come back and we'll start talking. We'll switch topics. All right. Okay, put Facebook away. Time to put your laptops away. So, let's switch gears a little bit now that we've got paging, page translation, and TLBs to make it fast, and now let's talk about what to do with it. So the first thing I want to talk about here is this notion of demand paging. And one data point to note is that modern programs require a lot of memory, and it keeps growing. So just like you have a Moore's law growth in transistors and a Joy's law growth in performance that leveled out in 2002, but still Moore's law is adding more processors, you've got kind of a Moore's law growth in amount of memory. And it's kind of interesting. I have people that I went to school with that are in the heart of Intel, and when they went from processor to processor to processor, they have a set of benchmarks that come from, say, Microsoft that they run to make sure they work. And they often find that the memory footprint doubles, every time they get a new release and a new processor. Okay, and so that's pretty crazy, right? And now, how many people have bought a computer recently that had 4 gigabytes or more of memory? Okay, that would be unheard of just 4 years ago or 5 years ago. Okay, so despite the fact, though, that programs are big, they don't necessarily use all their memory all the time. And so this is the typical 90-10 rule, which is programs spend 90% of their time in 10% of their code. And it's kind of wasteful to put all of that in memory at once. And so that's where paging comes into play. And remember that little diagram I showed you at the beginning of the lecture with registers, first level cache, second level cache, DRAM, and then disk. Okay? And so what we want to do in the rest of this lecture and the beginning of the next lecture is talk about using the disk to represent the memory we're going to use, and DRAM becomes a cache on the disk. Okay? And so basically, the solution here is DRAM is no longer the memory, the main memory in the sense that we've been thinking about before. It's really just a cache on disk, which is the main memory. And remember, the trick is we want to have the speed of the DRAM with the size of the disk. And that's going to be requiring some sort of locality to work to have this be even sort of an option. Okay? Any of you run into a good situation or a situation where there's not enough locality and this doesn't work at all? Anybody stuck in paging ever? Okay, now you may not know you were stuck in paging, but a good way to know is you watch the little disk light on your computer and it's doing nothing but flashing and everything's moving really slowly. What's happening there is that's a situation where there's no locality, and the only thing that's happening is data is going in and out of disk, and you're not actually executing anything. Okay? Now, so we want to give the illusion that we have infinite memory, or at least memory the size of the maximum address space, okay, even though we have a smaller physical memory. Now, I probably should have updated this for a 64-bit address space, which would really show the illusion of infinite, and maybe made this 4 gig, but you get the point. So here we have only 512 megabytes of physical memory, and we want to look like we've got a lot of actual physical memory with a lot of processes as well. So each process has 4 gigabytes of memory. It would be kind of nice if we could fake it, and we only have 512 megabytes. Okay, and that's what we're going to try to deal with. And that's where the page table comes into play, because when we go to access this big address space, some of the pages we access will actually be mappable and in physical memory. Other ones will be out on disk. And the hope here is that the ones that we access most of the time are actually in DRAM, and the ones we access infrequently are out on disk. Okay, and if that isn't the case, then we're in trouble. Okay? So how big are disks today? 2 terabytes. Okay, that's actually a commodity disk. All right, you can go to Fry's and buy a 2 terabyte disk for not much. All right, it's pretty amusing. And bigger are on the way. So I think Seagate and a bunch of the other, Hitachi, all of these guys have 3+ terabyte disks on the way. So the idea of what we're going to do in the next little bit of the lecture is we're going to kind of set up a transparent level of indirection. So the operating system is going to mediate kind of between the program and the disk in a way to give us the illusion that we have all of this memory that we don't really have. And so we're going to use the operating system to deal with paging to fix this for us. Okay? And notice that the actual physical location of pages is not going to matter because of this translation level. Okay? So, demand paging, I didn't really say what demand paging is. So the idea is, on demand, I go to access a page. If it's not in memory, somebody pulls it in off the disk for me. So on demand, I get a page. Okay? So since it's a cache, we can ask the following questions. What's the block size of this cache? How much gets pulled in? Page. Okay? What was the block size of a hardware cache? We said 32 to 128 bytes, right? So the block size of this type of cache is a page in size. So 1K, 4K, whatever your page is. What's the organization of this cache? Is it direct map, set associative, fully associative? Well, are there any... Somebody make an argument for me as to why it is one of these three. Go for it.
Fully associative, you can use any portion of memory that you want. So, in that sense. But if you want to restrict it such that only these pages be in those parts of memory, then you would get a set associative for direct memory.
So, if you okay, I'll buy that. I'll almost buy what you said. So, if you look at the page tables that we have, are the page tables that we've been talking about, do they represent fully associative, set associative, or direct mapped? Why direct map? So you index it using, not the offset, the virtual page ID. But what do we point to after we've indexed? A page table entry, and are there any restrictions on which pages can be mapped to which virtual addresses? Think about that page table you drew for the test. Are there any restrictions on which page table entries can be in there? Okay, go ahead. Yeah. So you're getting hung up, everybody's getting hung up a little bit on the algorithm and not on the end result. Yeah, go for it. Yeah, so what would be the conclusion from that? Yeah, so I will say that what we've been talking about is fully associative for the following reason. The page tables we've been talking about, any virtual page can map to any physical page, and there are no restrictions. Remember when we were talking about direct mapped and fully associative, or two-way set associative, there were restrictions on which part of the cache a data item could go in. Whereas with fully associative, there are no restrictions. So I would actually say, barring whether your table has some funny formatting issues, it's basically a fully associative mapping. Okay, does everybody buy that with me? Okay, and really what I'm talking about here is the restrictions on which pages, physical pages, can map to which virtual pages. There are really no restrictions. Okay? Go ahead, ask a question. I'm seeing some not so convinced stares. All right, maybe I'll move on. So how do you find a page in the cache when you go to look it up? Well, remember in the hardware cache, we divided the bits up a certain way. We took the index, we looked that up in the hardware cache. We got a couple of possibilities. We compared the tags. How do we find a page in this particular item when we look it up? Yeah. Yeah, you take the virtual page number, you walk the page table. Well, first you check the TLB to see if it's already translated, and then otherwise you just go through the page table, okay, the way we've been talking about. Okay? What's the page replacement policy? Oh, is it LRU? Is it random? Is it something else? I'll let you say depends this time, but why do you say depends?
Depends if you want to use configurable. So you can probably set a data of a register to change it between one and another, depending if you know what your random access your data access is looks like.
Okay, so this is one that's kind of funny, right? Because there are actually lots of options. And remember I told you at the beginning of the lecture, we actually talk about policy misses because we could have lots of policies on replacement. So in fact, we're going to have to talk about replacement. That's going to be a significant topic. Okay, and what do I mean by replacement? I mean that when I pull a page in off of disk, I'm kicking some other page out. Which one do I pick? Okay, and if I pick a bad page, I could cause a lot of slowdown because maybe I need it right away. So I got to be really careful what my page replacement policy is. Okay? Now, what happens on a miss? Well, first of all, page fault. And then what? Yes? Probably pull it from disk. Okay? Although, we already gave you some interesting examples of doing something else. Remember copy on write? That was also mentioned on the test, right? That's an example where you get a fault, but the thing's already in memory, and what you do when you miss on a write is you actually copy it. Okay, so there are other things you might do on a miss except other than go to disk, but certainly going to disk is the default here from a paging or from a caching standpoint. What happens on a write? Do we do write through or write back? Yes. Write back. Why? That's right. Remember, what's the ratio between instructions and disk access time? About 1 million, plus or minus an order of magnitude. Okay? By the way, you know that astronomers, that's their standard thing, is plus or minus an order of magnitude, right? So I guess we can be astronomers in this case. So definitely write back, and that means we need a dirty bit. Okay, because it's possible the processor has written to a page and it's now dirty. If we're going to kick it out, we better write it back to disk, otherwise we're losing data. Okay? Any questions? Yes? Well, you tell me. So what are we actually talking about here? Are we talking about the DRAM or are we talking about something else? Yes? Yeah, so it's going to be in the page table entry. Because it's not the particular DRAM page that matters, but rather the fact that that mapping was used and has data in it. It's kind of like it's in the DRAM, but it's really associated with the page more than a DRAM item. Okay, good. So remember the PTE? Here's the one from the x86. I put this up a few lectures ago. Notice some things that we didn't note before very carefully. Here is, obviously there's the present bit, the writable bit, whether it's user accessible or not. But notice this, A. A is whether the page has been accessed or not. D is whether the page is dirty or not. Okay, so the A and the D bit are going to be very interesting for our replacement policy. Okay, can somebody explain to me, so what's the D bit good for? Write back, right? We just said that. If you've written the page, you need to know it's dirty. Now, most good hardware, what happens, remember how the MMU automatically takes a TLB miss, walks the page table with a hardware page, not nachos, and brings in the PTE automatically in hardware. This dirty bit typically gets set automatically in hardware as well. So when you go to do a store and it's already mapped, you know, the fact that you did a store gets altered, the PTE just gets altered to have the D bit set in hardware. So all we have to do when we're about ready to page something out is we just look at the D bit. If it's 1, then we have to actually write it back to disk first. Okay, questions on that? Somebody tell me why the A bit might be useful. Yes? Why is the A bit useful for replacement? Exactly. So the A bit lets us tell whether something's been used recently. So what we do is periodically we set all the A bits off, and then if anybody ever uses the data, the A bit gets set on, and oh, that page is live. Okay, so those are the A and the D bits. They're going to be very important to our replacement policy. Okay? Good. Questions? So the page table helps us implement demand paging. Why? Well, when the valid bit is set, we know the page is in memory, and the page table points at a physical page. That's the case where the hardware takes over and no software involved. If it's not valid, then the page is not in memory, and potentially we have to use some information to figure out where it is. And by the way, at least in the x86, this isn't always true, but if you set this bit to invalid, the other 31 bits are kind of available for you to do whatever you want with. And so in that case, the operating system could store some stuff there that says what disk block it was in. Okay? Even when it is valid, there's still typically a few bits the OS can use for something if it wants to. Something about the page. Okay. So suppose the user references the page with an invalid PTE. What happens? Well, one option, first the memory management unit traps to the operating system. That's a page fault. And then what does it do on a page fault? Well, the operating system figures out what an old page is that needs to be replaced. If the old page is modified, it writes it back to disk. It changes the page table entry of that old thing to be invalid and gets rid of the TLB entry, flushes it. So notice that all we've done now is we've kicked a page out. So we're doing a lot of work to make the page invalid. Then we load the new page into memory. We update its page table entry to be valid, and now we invalidate the TLB for that new page. Can somebody tell me why we have to invalidate the TLB for the new page that we just pulled in? Yes? How was it different the last time? When was the exact last time we accessed it? It's on this screen. Yes? Yeah, so we accessed it and we got an invalid PTE. So there's an invalid PTE in the TLB. Boy, I sound like I'm spouting acronyms at you guys. Right? So the page table entry for the address we just accessed is invalid and possibly in the TLB. So we got to kick it out because we've just updated it to be valid in memory. And what we want is we want to retry the access that failed and have it fault in the TLB, walk the page table, see that it's valid, and now we're good to go. Okay? Do you hear me? I'm just kidding. So, and then when we're done, we continue and we're good to go. Okay, so this part here is the caching aspect. Yeah, go for it.
Can you explain what you mean when you say change its PTE and then cache TLB?
So what I'm saying here is we've picked a page to kick out of memory. And as a result, what does it mean to kick it out of memory? It means that it was originally mapped to somebody, and we're making it unmapped. So that means we're writing it to disk, and then we've got to mark the page table as being invalid so that we won't accidentally think that we can make an access. And that's what we mean by changing the page table entry to be invalid. And then we've got to flush the TLB because it may be in the TLB as valid as well.
Why don't you just go through the TLB and invalidate that entry?
Well, I actually said, I just said TLB is invalidated. So this is implying that if you could pick that one out, you just do it.
Does this also mean that the operating system needs to have a mapping of every process to every process page table, or like ways to get at every process page table so you can go to that specific process page table and modify it?
Yes. So you're asking, when I do this kick out, how do I figure out which page table it's in? Okay, now, in the simple case, if we never allow sharing of pages, then we could have exactly one process that holds that page, and we could have a structure in the kernel that says that one page goes to this one process. In reality, since we allow sharing, we need to be more general. And there's typically this notion called a core map, which we'll talk about a little bit later, where you can take any physical page and say, give me all the page tables that this is in so I can walk through them and invalidate them. So it's kind of a reverse direction. Good question. And so the TLB for the new page is loaded when the thread is continued. And the other thing to note is that this is not continuous because we've got a disk access in here. So if we were to stop everything just so we could do a disk access, this would be bad. So what we do is while we're busy loading new page into memory from disk, we're actually switched out and another process is running. Okay? Because when we're page faulting on process A, why hold everybody else up? We'll let process B run. Okay? Questions? All right, good. I think this is a great place to break. So in conclusion, the TLB is a cache on translations, fully associative to reduce conflicts, and it can be overlapped with the cache access. I showed you how that can happen. Demand paging is really this process of treating memory as a cache on disk. So a cache miss in this case is get page from disk. We're trying to set up a transparent level of indirection so the user program never has to know that page faults are occurring. All that really happens is it runs more slowly. Okay? We talked about this interesting thing about a software-loaded TLB where the fast path is handled in hardware, that's a hit, and the slow path is a trap to software to actually do the page table scan. This is project 3. You get to do this. Okay? Yay. And next time we'll finish up on talk about precise exceptions. All right. Have a great weekend. See you next time.